Hi, everybody. I'm Paul Jungwirth. I do freelance development and consulting through my company, Illuminated Computing. My favorite work is Postgres work. I've been a minor contributor to Postgres since 2016. I worked on multi-ranges, and since then I've been working on adding application time support for temporal tables following the SQL 2011 standard. As a newish contributor, I've often wanted a comprehensive guide to contributing to Postgres. There are many excellent talks and articles out there already, but I've never found one that really touched on the executor phase. And it's such a huge system, nothing can really cover everything. So this talk is the bits that I had to figure out on my own, and that I wish there had already been a talk about these things. So before I dive into the detail, here's a map of the territory. To execute a query, Postgres is going to go through all these phases. It has to parse your SQL, make sure it makes sense, apply rewrite rules, build some plans, cost them, and finally execute everything. Lots of the talks out there already talk about the parsing and analysis phase or writing custom C functions. And those are an excellent place to start, probably better than this talk. But I wanted to talk about especially the executor phase, which is where the real work is supposed to happen, right? So I'm going to go through all of this, but I will rush through the first parts and slow down as I get to the end. It's going to be desultory and digressive, but hopefully two things will help. I will follow this pipeline as a structure, and I'll use my recent temporal work as a writing example to help give you concrete examples. Here's the temporal stuff that I'll be using. There's 4 parts. First of all, you can define a period on your table. You can create temporal primary keys and unique constraints. You can give a temporal update or a temporal delete, and you can create temporal foreign keys. 95% of what I'm going to talk about is just this here. And that's because the other 3 are DDL commands, which skip much of the query pipeline. Only DML commands like this or select get the full experience. Here's a quick visualization of what for portion of does. In the SQL 2011 standard, it says that we've got an old record with time bounds, and we want to update just a portion of it, which we give in the syntax at the top when we say for portion of. And what we need to do is save the updated version of the row with updated timestamps. And then to preserve the untouched time periods, we insert 0, 1, or 2 new rows that equal the old previous values of the row. And those are our leftovers. So that's what we're trying to accomplish here. This is the only picture you get the whole talk, so I hope you're ready. Now, why do these phases matter? I've seen many patches whose first version was returned with similar feedback to this, where everybody wants to do as much work as possible in the analysis phase, which makes sense because Postgres already has all these great features. If we can implement our new patch in terms of those things, then we just have to do some work in the analysis phase. We don't have to even learn anything about the other phases, and it's great. But it's not really the right way to add functionality to the database. Here's something that Tom wrote back in 2017. Robert Haas has a similar, very long patch review from 2019 on an early version of the merge command patch with lots of specific reasons and citations. They're both linked in the references at the end of my talk. For years, actually, I remembered these posts and wanted to go back and find them, and I could never find them. Finally, for this talk, I downloaded all of the inbox files off of the archive site. Sorry about that. But I think that they were too good of feedback in a general sense to just get lost. And so they're linked from the talk, and I think it'd be great to link them from the Postgres wiki page also. So what's really wrong with doing all of your work up front in analysis? I mean, besides just having a sensible code organization, there's concrete problems that you might not be aware of. For instance, if you describe a view, you want to see the SQL that you typed, more or less, and not some other thing. Or similarly, if you run explain on your query, then you want to see things that you recognize. My own work actually does add a where condition when you run for portion of. It makes sure that we only hit the rows that would overlap with your from and to bounds, which helps to make sure that we use an appropriate index and we aren't doing extra work. And that does appear in the explain output. I think in that case, that's a sensible decision, but it's something that you should think about. You know, am I adding things that will be a surprise to the user when they run explain? Earlier in the patch, I had another problem where I was requiring a primary key to use for a portion of, which is not really correct, so I changed that. But I noticed that if you ran for a portion of against an updatable view, then it failed because we don't resolve the view until later, until the rewrite phase, right? So it's looking for a primary key. The view doesn't have a primary key, so we got a failure there. Here are some of the major functions that Postgres calls on its journey through the pipeline. We've got parsing, analysis, rewriting, PG rewrite query, query rewrite, and rewrite query, planning, setting up executor nodes, and finally running the executor nodes. So let's start with parsing. Postgres uses Lex and Yak, or I should say Flex and Bison, to tokenize and parse your input. The Bison file is all in gram.y, which defines the SQL grammar. Here's a quote from my patch, adding for portion of functionality. If you've never seen this before, if the input matches the rules at the top, then Bison will run your C code, and these little dollar signs get updated. You can see in here a call to make node. Parsing constructs this big tree of nodes for all the different bits of your input. And the nodes are what flow through the pipeline. We start with parse nodes, we'll turn those into plan nodes, and then we'll build executor nodes. In my case, here's the definition of this new node for portion of clause. There's big high-level nodes, like for the select statement, down through nodes for clauses like group by and over, and little tiny nodes for like chopping up all the bits of an expression, operators, function calls, literals, column references, etc. And then there's functions to make a node, like make node as we saw before, which is allocates memory for it, to copy a node, to print a node, to read a node back from what you printed. Until recently, you had to write all of these yourself. Now there's some clever code gen that does a lot of this for you. There's still a little bit of tree walking code you might have to, with big select statements, where you might have to handle your new node. But it's easy to find those things by looking for other nodes already that maybe do something adjacent to what you want to do. You'll also see many things using a type called list. And a list is also a node, but it's a node that has a bunch of other nodes. There's functions to build lists, iterate over lists, append to a list, and you see these all over the code base. When people say that Postgres is Lispy, I imagine this is kind of what they're talking about. I would actually love to see a lightning talk on Postgres' Lisp history, maybe next year if anyone wants to do that. But nodes and lists are well covered by other talks. So if you want to learn more, there's a lot of references at the end you can look at. So all these nodes are getting allocated, right? And this is C, right? So we have to free them. But actually, we don't. Postgres has an arena-based memory system. And these arenas are nested. And when you get to the end of one, then we throw away everything that's in it. There's a big instance for the transaction, for the current statement in the transaction. For each row, as you're processing it, if you call a function, you're going to have an arena for the function call. For someone like me who writes a lot of Ruby and Python, this is amazing, right? Just the total insouciance about memory management makes me like want to write more and more Postgres. And if you also are used to memory-safe languages, this is it makes Postgres hacking very comfortable. There are some places where you still have to care about memory, but for the most part, it's way easier than C development that you may be used to. All right, so the Bison file gives you a big tree of what was typed, but we haven't done any work yet to like look up the column names, make sure they exist, turn them into OIDs. Same with the table names and function names. Do validations, maybe check some permissions. All of that happens in the analysis phase. And it's going to transform your initial node tree, in this case, an update statement is our input, into a query node tree. You can see that we have this transform update statement, and we start out by making a query node. The first thing we're going to do is we're going to look up the table that we're trying to update. Here, we're handling the for portion of clause. We feed in our for portion of clause node. We get back a new node called a for portion of expression, which has the OIDs that match the columns, that kind of thing. Also, it'll build an expression to take that from and that to and turn it into a range type for us, which we'll use in various parts of executing. A lot of this analysis work happens in functions named transform this, transform that. Here's a transform from clause. But maybe you notice that we're not using the return value at all, right? So that's interesting. But we are passing in this top-level parse state. And parse state has a struct with a list member that holds all these range table entries. Range table entries are something that you'll see all over the place. Later, we'll move these range table entries over into the query that we are building that we saw earlier. So what are these range tables? The name was very confusing to me at first because the range is not a range type, and the table is not a database table. Actually, the range means table, or I should say relation, and the table is like a list of structs. So this is one entry in that list of structs, which we'll call a table. Each of these ranges is maybe a physical table on disk, maybe the result of a subquery or a join, maybe something more exotic like a set returning function. It's very flexible. So when your query is joining a bunch of tables or other things, each from entry there is going to give you a range table entry. Now, another thing that you use in analysis a lot, but also anywhere, is the syscache. The syscache lets you look things up in the system catalog tables, the PG underscore tables. Here's for portion of looking up the period name. Here we call this search syscache 2. The period name in caps is the name of the cache, which I added by editing the syscache.c file. And when you do that, you don't have to implement all of the cache yourself. It's very declarative. You give the name of the cache, the table that you're looking in, an index to use, and the things to compare against. In my case, I want to compare against the table, which is the relation ID, and the period name, which uniquely gives me a period, right? And then I can call it here. You don't necessarily give a result. So if something goes wrong, we'll report an error. And then we cast the result. We get a heap tuple, which we can cast to a struct that is exactly like that table layout. This line is kind of amazing, actually. I'll come back to it. For simple types like ints and OIDs, we just pull them off the struct. When we're done, we call release syscache. This isn't freeing memory, but it decrements a reference count so that Postgres knows when it can unlock the cache entry. If you don't call it, it will still get unlocked at the end of the transaction. If I recall correctly, Postgres will scold you if it has to do that, though. For fancier things than ints and OIDs, there's helper functions that you can use. For instance, here, I'm getting a type. Actually, this is kind of a funny example because type is just a type def for heap tuple. And so I can pull something up. You have to free it the same way, and I can pull something else off of it, like a string. Another kind of type is the L syscache. I don't know what the L stands for. Maybe somebody could tell me. It's got a bunch of common helper routines to help you on top of syscache. They call release syscache for you, so they're very convenient. And they're also very common to use during analysis. Here's a function that I added to the L syscache, which I use over in the foreign key triggers part of the code. And basically, every function in L syscache looks the same way. It's going to search the syscache, pull something off of that struct, release the syscache entry. It's very common to see this pattern where you can fail or not fail depending on the caller's preference if you found something, and then return the result. So usually, if you want just like one thing off of a catalog table, then it's common to have an L syscache helper. If you need a whole bunch of things off of that row, then you would just use the syscache directly. And then the last cache that you will surely need to use is type cache. Types and operators are so important, you can hardly do anything without type or an operator being involved. But their information is spread out over all these tables, right? There's PG type and operator and mop and op class and op family. So it would be expensive if we had to build this up every single time by querying all these system tables. In the type cache, almost the only function that you ever really need to call is lookup type cache. And it gives you a type cache entry. Type cache entry is a huge struct, and you don't always need all of the things. And so you can pass some flags to say what information you care about for that type. A type cache entry is never actually freed. Postgres assumes that types don't change very often, and so it doesn't need to free them. So you see there's no like release or free or anything like that happening here. I guess if you built an application that operationally defined types and redefined types, then you would probably run out of memory in Postgres, but hopefully no one is doing that. Here we're just pulling off the types, type size and whether or not it's passed by value so that we can make a copy of the range. All right. Here's a little bit more from my analysis code. We want to build an expression from the targeted range. So I mentioned this before. We want to get the individual bounds as nodes. Actually, this function transform for a portion of bound. Almost doesn't need to be a function, but we do want to handle a special keyword here to support an unbounded use case. Next, we will make a function call node, which is calling a range constructor of the appropriate type, passing in the bounds. So we're building our range here. Not actually building it, we're just setting up the node tree to build it. Range name location is something that you see a lot in Bison code, which just gives the user a pointer to where an error happened if we need to report an error. And finally, we call transform on this expression node also. One thing this does is make sure that we're not using unsupported features inside of this expression. That's the exp_kind update portion. So this will go through and make sure that everything inside of this expression is allowed in this context, right? So you're not allowed to do a big subquery here or a window function, that kind of thing. And we stick this expression on our struct so that we can use it later. Here we've got some code to set the new bounds on the record. We take the old bounds and we intersect them with the targeted range. So this is implementing setting the bounds on the updated record. And you can see that we're making this target entry, or a TLE, target list entry, is how it's often referred to as. In an update query, you'll have one TLE for each column that you're setting. In the select query, you'll have one TLE for each column that you're selecting. So it's reused in these different contexts. A TLE is a lot like a range table entry, actually. It's the same kind of pattern. It's one struct in a list of structs. All right, that takes us through the analysis phase. The rewriting phase is next. What we do here mostly is expand views. We apply rules, which we're all discouraged to use. The main functions here take in a query node, and they give out a list of 0 or more query nodes. In the really easy cases, we're just wrapping the passed-in query in a list, in fact. So I did have to do a little bit here so that you can use for portion of against an updatable view. Postgres has this idea that if there's a view, and if it's simple enough, you can actually write an update against it instead of against the base relation, which is pretty cool. And I wanted to make that work with for portion of also, which means that I have to remap the attribute number of the range that you're trying to set the bounds of. So we have it for each of those things. It might be, in this case, it's just going to be 1 because it's a range. For each one, we've got a target list entry, which we're pulling off. And then we need to remap that target list entry from the views position to the base tables relation. Now for planning and optimizing, for each query node, the planner will give us back a planned statement node. So now we're transitioning from our parse nodes to our plan nodes. There's an abstract superclass plan node, which are, and the so-called subclasses of it are things that you might recognize from explain output. Things like joins and sorts, CTE scan. On the other hand, there are a lot of node types that are shared between parsing and planning. For instance, range table entry, target entry, bits of expression things. In my own patch, there's about 1 line here just to copy my thing from the parse tree to the plan tree. And if you don't have to do a lot of work here, then your patch might be similar. But you can do more transformation here if you want. The include files are give a nice separation between what's a plan node and what's a parse node. There's a primnode.h, which is primitive nodes, which are things that are often shared. And there's an execnodes.h also. You probably have to do at least like 1 line here, as I did, just to move your stuff over. The real work of this whole phase is to find the best way to implement your plan. For each table in your query, the planner will generate multiple paths, which are how do I get the rows out of this table? Is it a full table scan? Is it an index scan? And then for each join, the query will generate paths, and then it will cost all these paths and choose whatever looks like the best choice. If you're working on optimizations, then that's probably code you'll have to dig into. I didn't have to look at any of that, so I don't have too much to say here. When I worked on multi-ranges, I did have to do a tiny bit of work here where each type has ways to compute statistics about columns of that type, and you can save those statistics, and then you can compute selectivity estimates based on your statistics. So I did touch a little bit of things there. That's all I know about the planner. So once we're ready to run the query, we pass our plan tree to the executor phase. This goes through a portal, which is just the door that passes our rows to the client program or maybe to standard out. We don't have to talk about it here. If you are interested in cursors, that's where cursors are implemented. That will call executor start and executor run. Executor start sets up another node tree. This is all of our executor nodes. Create executor state will create an eState struct that will be used by all of the execution. Most plan nodes require some kind of mutable state to run and do their thing. So they need to create a corresponding plan state node. It's called plan state. I'll just refer to them as executor nodes. And they're like counterparts. A plan node needs to be stable during the execution. You can't write to it. But a plan state is a place where you can make changes as you are executing your feature. So you can imagine these parallel trees. Here, we need to call exec init modify table. What we call exec init this and exec init that, whatever node type that we have that needs to set itself up. And then exec init node, which you see here, has a big switch statement, which knows which exec init to call for which node type. And each of those node types, if they have children, they'll recursively call the appropriate exec init for their children. Or maybe they don't care what kind of node their child is. Like in the case of modified table, it could be getting rows. It could have a child that is feeding it rows, but maybe it's one kind of node if it's an insert, or another kind of node if it's an update. And so it can call exec init node again, which knows how to dispatch to the right place. And then finally, executor run will do all the work. There's also executor finish and executor end, but you can look at those on your own. They're less interesting. So here's the plan state node that I mentioned, and all of our executor nodes basically inherit from this. Each one has a type, like any node. Each gets a reference to its counterpart plan node. They all reference that eState struct that I mentioned. And then they also all have a function pointer, which tells how to actually process a node of this type. So in actually doing the execution, actually running the executor, we're going to be calling these functions. There's lots more in this struct, but this is the main idea. Here's a little bit of what we do to init our for portion of work. So we're not running the row by row update yet. We're just initting the node. This happens inside of exec init modify table. We need to evaluate this expression that we built with the from and the to parameters. So now that we're doing execution, now is our chance to do that evaluation. And those don't need to change row by row, right? They're stable for the whole update command. So we do it here in the init section. Let's see. OK, another thing that we do in the init step is to set up some tuple table slots. A tuple table slot is a place to hold a tuple. We saw this very briefly before. And we need a place for 3 tuples. We need a place for the old row before we changed it. We need a place for the row we're going to possibly insert for prior time, and the row we're going to possibly insert for post time. So we create 3 tuple table slots here. I'm going to say a lot more about tuple table slots in a minute. But here, just look at what we're doing. We create the first one with table slot create. And then we create the other ones with exec init extra tuple slot. So there's a difference in how we're setting these up. OK, so that's executor start, which gets us ready to call executor run. This calls execute plan. And then you can see it's going to just loop forever. And as long as there's a child node feeding it tuples, it's going to keep going. And when that is done feeding it tuples, then we're finished. Inside this loop, we're going to call exec proc node, which is just an inline function that chases this function pointer that we saw before. The result is a tuple table slot, which is basically how all of these nodes communicate. They're always passing one tuple at a time back to each other. For instance, you might have a node that does a nested loop, which you've probably seen in your explain output. It's got an inner relation and an outer relation, and it needs to call both of them. And this is how it does it. Each time it will call the exec node's function pointer, get a tuple table slot, and do what it needs to do, and then call them again. So we've got this whole tree of proc functions, all passing around tuples between themselves. Incidentally, using function pointers has a side benefit, which makes it easy to inject instrumentation. I haven't looked this up, but I'm pretty sure this is how explain analyze works. OK, here are some bits from exec modify table now. As you can see, this is also just looping forever, asking its child node for tuples, and then doing its thing with those tuples. And this is the same code for insert, update, delete, and now merge also. But then it will do the right thing for each of those cases. Exec update will call exec update prologue, exec update act, and exec update epilogue. And the for portion of work we need to do happens in the epilogue. So that's here. We are finding out if there are any leftovers, and then we'll insert rows for those if we need to. First, we're going to get the row's old range value. We call slot get adder to do this. That will get us the target range using this datum function. Then we'll find out if there are any leftovers to the left or to the right. So these referenced variables get set. And now we have a couple more range type instances. Now, if either of those are non-empty, we'll insert rows for them. We'll take the old pre-update values. We'll copy them into our tuple table slot. We'll change the start and end values, and we'll do an insert with this. All this uses tuple table slots. So let me talk about those, and then I'll come back here and go through this code again more slowly. OK, if you're doing any work in the executor, you probably need to deal with tuple table slots. And I couldn't find any talk or article anywhere talking about these things. Fortunately, Postgres has excellent comments, and almost every directory has a README in it with a very nice overview. So you can figure it out, but I thought it would be great to give a talk on it. So a tuple, of course, is more or less a row, and a tuple table is how the executor deals with processing these tuples. And it's a table of slots, just like range table entry is a table of relations. So we've seen three things so far that all have the same pattern: a target list entry, a range table entry, and a tuple table slot. Each tuple here gets kept in a tuple table slot. A tuple table slot is also a node, right? We've got a node type. And many of the exec nodes have these as members. We've also got a list of datums and null flags. Every other intro to Postgres talk talks about datums. So I've kind of shied away from giving too much information. If you were in the FDW talk earlier today, you would have heard a little bit about datums. Basically, they're 64 bits wide, maybe 32 bits, and either have the value itself, if it fits, or otherwise a pointer to more data. They don't tell you what kind of data they're holding, so you have to know that through some side channel. And then there's functions and macros to convert them to and from concrete types in C, like datum get int 64, int 64 you get datum. We'll put it back again. If the data is toasted, then that will detoast it for you. Lots of links in my references will give you more details if you want to know more here. So these two arrays let us get at all the data in the tuple, but then there's lots more information here about the tuple as well. We have a tuple descriptor, which tells us how many attributes there are and what their types are. In fact, if possible, you will just have the whole PG attribute record in here. We have a reference to a memory context, which is where we allocated the slot, but not necessarily where we allocated the tuple. And then there's actually 4 kinds of tuple table slots, which are distinguished by this TTS ops field. This points to a struct with a whole bunch of function pointers that tell us how do we implement various things that this tuple table slot can do. So this is our dynamic dispatch. OK, one of the types is a heap tuple table slot. Here is our C-style inheritance. We're a so-called subclass of tuple table slot. We have a reference to a heap tuple, and that's got the memory that actually is the tuple. A heap tuple table slot points to p-alloct memory, so that's what's going to be in there. If you want to get something out, you can call slot getAttr, which we were doing a little while ago. Actually, that is going to call one of those function pointers on the ops struct. In the case of heap slots, it's going to pull the data out of the heap tuple. It's going to cache it in that datum and isNull array that you saw earlier. So jumping back to our code from the init node, here we are calling slot getAttr. And as long as we're talking about heap tuples, here's some code that I've mentioned before. Back when we were calling syscache, we were getting heap tuples. So this isn't a slot, which is really just something we use in the executor. It's just the tuple itself. And then this line that I mentioned, getStruct is really just adding a little pointer offset. And then we cast it to the form of our table, which is amazing to me. And this works because we have a compile time definition of our catalog tables, right? But for user tables, we have to call slot getAttr. Here's the next type of tuple table slot, a buffer heap tuple table slot. So this is very similar, but whereas a heap tuple table slot is in p-alloct memory, a buffer heap tuple table slot lives in shared buffers, basically, lives in our buffered memory. In fact, that heap tuple we were getting from syscache should be one of these. For these tuples, we need to take and release buffer pins, not alloc and free memory. A pin is something that says, hey, don't throw this buffer page away. I'm using it right now, right? Just like sticking a pin in a card and pinning it to the wall. This is kind of the normal case, I would say, in the executor, as far as I can tell. It's the most complicated. You can see it's sort of like a subclass of, heap tuple, as a matter of fact. And in some ways, I think that this use case maybe explains why we even have tuple table slots in the first place. It lets us have child nodes that are finding things in the buffer cache and then handing them up to nodes further up the tree, which will also refer to that data with their own tuple table slots. Next, we have minimal tuples. This is a lot like a heap tuple table slot, except that there's no system columns. There's also a header struct that we skip. You might use these for computed tuples that don't come from the disk. I don't totally understand minimal tuples, to be honest. So I looked around at where we use them, and I saw that we were using them with hash joins a lot, with aggregates and group by. Even though it's not from a system table, it still stores its data in a heap tuple struct, right? So the data is formatted the same way. And then the last type of tuple table slot is a virtual tuple table slot. This is something that doesn't have its own tuple storage. The datum and isNull arrays are the authoritative source of truth in this case. This can be a nice optimization to prevent copying. For instance, maybe the child node is using buffer heap tuple table slots, and then up above we can use virtual tuple tables slots, so we don't have to copy that data, right? We can just get it from the same place. You can also use these for computed data by setting up the data is null arrays yourself, and then going and doing something with that tuple, like inserting it. So here we're making a couple of these virtual tuple table slots for our leftovers. And then I think it's interesting to compare the top and the bottom. Table slot create will give us a slot that matches the relation we pass in. So here we expect to be just getting buffer heap tuple table slots. In all three cases, we need a tuple descriptor, right, that tells us what are all of the things in the tuple. The lower functions, we pass that by hand. That's tupdesc there. In the upper case, we can pull it off of the relation because we're just making it based on a relation. And then finally, where do these tuples go? They go in the tuple table. At the top, you see that we're passing ES tuple table, which is part of the executor state, the top level executor state. So this is our list of all of these tuple tables that we are generating during the whole executor process. It's a list node, and it's got a bunch of these tuple table slots. And to me personally, it's just a little reassuring to get a glimpse of where we're putting them. In the bottom, we're also passing the executor state, and this function knows to take that struct member and put the tuples there. OK, so there's a whole lot of functions that say what you can do with tuple table slots. Create them, put a tuple in, get a tuple out. To see the API service, I would go and look at the include file. But here are some examples of what we can do with them using for portion of. The first thing we're going to do is pull the old version of the row out of our tuple table slot. And this should just basically hand us the reference and not really do anything. If we had said true instead of false, this would materialize the tuple table slot, which makes the slot like the owner of the tuple and will copy things into its memory context if it needs to. But we don't need to do that because we're about to make a copy of this anyway. Here, we copy this tuple into our virtual tuple. So this will set the datum in is null arrays. If some of the datums are passed by reference, they're still pointing back into this heap tuple, though, right? Which is not really our memory. Next, we will use that to compute the new start and end times. This is going to put a different range into our datum array, or if we've got a period, into the columns. And finally, we call exec materialize slot to make the tuple ready. As a virtual slot, so all these functions will use the ops field of the tuple to chase a function pointer and do whatever is right for that type of tuple. So that's we have a nice kind of polymorphism happening. In the case of a virtual tuple, what this will do is look at all of the datums. And if any of them are passed by reference, it will make sure to copy their memory into the current memory context. Well, into the slot's memory context, I should say. So now we've got our own tuple. It's not pointing into anyone else's memory, and we're ready to use it. And that means that we can insert it. All right, so that's the end of our journey. Thank you for listening. Here are some references. I learned a ton from these talks and articles. I skipped a lot of stuff, which is very well covered here. So I encourage you, if you're interested in Postgres contribution, to take a look at these. Last on here is the GitHub repo for this talk also. And I'm happy to answer questions, or giving a talk like this is also a good way to provoke a code review if no one has looked at your patch for a while. So any corrections are also very welcome. Yes?
The first question would be about the status of your patch. So you partially answered this, but so does it mean that your patch is now ready to be reviewed?
I've had a couple reviews recently, and so I've got some more work to do to make some changes. The status, yeah.
It hasn't been yet approved, so
No, no.
probably.
Maybe 17. I'm hopeful about 17.
Okay.
Yes.
How does it handle the returning clause when one updated row returns 3?
Returning does not return the inserted rows. It just returns the row that was updated. Because semantically, the inserted rows are what didn't change, right? It's like what didn't happen. All right, well, thank you for your attention, and I hope you enjoyed the talk.